So that's section 4.2, the graph of polynomial functions. And what we're going to study here is graphs of monomials. And using that, we're going to enter general polynomials and understand the near zero behavior of the graph. And after that, we enter the end behavior of the graph. So here's a graph of monomials. They look like this, and I'm going to copy that. So this part is the graphs of monomials. Monomials are, polynomial is in that shape: x to the first, x to the second, x to the third, x to the fourth. It's all commas, not plus, so polynomial has only one term, right? That's called monomial. The simplest one is y equals x. Everybody knows the graph of this one. And this is also very well known to students. Y equals x squared. X cubed here, if you haven't seen or don't remember how this one looks like, let's plug x equals 1 in there as 1 to the third. So that's 1 there, right? And I'm going to try 1/2 right in the middle and see what happens if you raise 1/2 there to the third power. What do you get? 1/8, right? And this one here, if you plug in 1/2 right there, if you square that, it only gets you 1/4. Which one is smaller? 1/8 is smaller, right? So if you look at 1/2 point up there, and same 1/2 point up there, this is a lower. If you look at this shape, it's kind of similar, but you can see that it's slightly different. And as you get higher and higher power, what happened to this part? It always is 1. Whatever power you raise this 1 is always 1 in here. What happens is that for the same point 1/2 and 1/2 and 1/2, as you raise in higher and higher power, this is coming down lower and lower and lower. And this is also described more globally that here is kind of pointy shape. And if you look at here, it's kind of flattened out a little bit. If you even raise the higher power, it's even the flat part is even longer. And if you look at the fifth power, this flat part is even longer. But all of the cases make this sharp turn had to arrive 1, right? No matter how long you stay at the bottom here, you have to make a sharp turn to get to the 1, 1. That's one description of what is happening in the first quadrant. If you look at the odd powers here, x to the third and x to the fifth here, if you try -1, third power, you know it's going to be -1, right? Because third power. So it is actually down there. But if you look at even power, if you raise -1 to the even power, you know it's a +1. So this direction is remaining above the x-axis. And the same thing is happening for x to the fourth. Is above x-axis. And the odd power is down there below the x-axis. So I want you to understand these simple behavior because we're going to use that to sketch the graph of other type of function. If it is x to the first, straight line, right? If it's y equals x squared, it looks like this. X cubed and had x to the fifth has a similar behavior. If it is higher power, try to introduce a little bit of a flat part around that 0. If it is higher power for even, try to introduce a little bit of a flatter part in there. That's how you're going to sketch these things. Fair enough? All right. If this is like this, you know how this y equals -x squared looks like, right? It's flipped down across x-axis. And if it is y equals -x cubed, then it was flipped down in here, upside down across x-axis, reflected shape. These are the graphs of a monomial. Fair enough? And also, generate this computer image to compare the curvature of this one around x equals 0 clearly. So this is blue one is y equals x. Orange one is y equals x squared. As you can see, this and not x squared is x to the third, and this green one x to the fifth. As you can see, its flat part is longer in here, right? And this is even power. This blue one is y equals x squared, and orange one, I think, is y equals x to the fourth. The green one is y equals x to the sixth or something, right? So you keep second down like that. I think that part's easy. So what's going to happen in general, that is not just x squared and x to the third, you have x to the fourth plus whatever in general polynomial. We're going to look at the zeros of this polynomial. Do you know how to find the zero of a polynomial? You factor, right? You factor and then there are the zeros. So after you factor that, you go to the zeros and determine how it looks like. It looks like this odd degree monomial or even degree monomial, right? It is missing y equals x there, right? But it does happen. So this is the building block of how we sketch the graph using the zeros, right? So here is principle. Before I enter that, I have actual computer image I generated. This is a graph of a function who is already factored. X minus 3 cubed here, x minus 2 squared, and x minus 1. Right? I sketched it. So x equals 1 is a 0, right? So if you go x equals 1, and that's the shape in here. If you zoom into that one, it looks like this. This is x equals 1, and it crosses like that. If you zoom in even further, would you agree that looks a lot like a straight line? Right? So if you go back, if you ignore other parts, you're left with x minus 1. That's a straight line, right? X equals 2 is another 0. If you go x equals 2, and it looks like a parabola down there. So if you zoom in, x equals 2, it actually looks like the square shape there. X equals negative x squared. So next to 0 is x minus 3, the raised to the third power. It's a shift of x equals x to the third. So if you go there, it's difficult to see how it looks like. So I zoomed in like that. It looks like y equals x cubed, right? Slightly stretched version, but overall has that shape. So if you see the factored form, you know already how it looks like. It's a matter of is that down there or up there, right? You know the shape from this exponent called multiplicity. So 3 is a multiplicity of a 0, 3, and exponent 2 is a multiplicity of 0, 2, and here's invisible 1 is a multiplicity of 1, right? So polynomial is given, you factor it like this, go to 0 and sketch this shape by looking at this exponent and try to connect it as simple as possible. Alright, so I'm going to use this example to actually how to do these problems. In the test, I'm going to ask you the strange question they don't usually ask, which is computing approximation, and that's help you to understand why it works like that. So I'm going to phrase it like this: compute approximation near zeros. Okay? So if you figure out how to sketch this one quickly, it doesn't matter, you have to understand this principle in here. So here's how it goes. What are the smallest zeros you see here? Negative 2, right? Negative 2 is a 0. So x equals negative 2 will be description with 0, right? But we want to describe approximation near 0, so I'm going to use this expression like this: negative 2. X is not exactly negative 2, but close to negative 2. That's what that symbol means. Then px, that polynomial they gave you, is exactly that. We have that expression, but I'm going to simplify with the approximation. So it is approximately equal to, right? So x is negative 2. You can just replace x equals negative 2. That's the approximation. But if you plug in x equals negative 2 here, you get 0, right? No matter what you plug in here, everything is 0. So that is not incorrect. It's just no information. So don't touch that factor that is related to our 0 part. So you leave it there. Don't touch that part. But you can plug in x equals negative 2 is correctly predicted. So what happened if you plug in x equals negative 2 there? Negative 3, right? Putting negative 2 there. negative 5. So I'm claiming that around x equals negative 2, px behaves like, polynomial behaves a lot like this polynomial, right? Simplified. Because x is close to negative 2, so if you plug in negative 2, you're sure it's close to negative 3, so it's approximation. If you replace that approximation with a 0, is it too much simplification? So what is this one in here? 15 times x plus 2, right? So around x equals negative 2, this polynomial behaves like this line with x-intercept negative 2 with the slope 15. Okay? So number 2, what is next in the number line? The 0 in here. Positive 1, right? So it's positive 1. So px is approximately, and which one we're not going to touch in here? This one, right? If you plug in x equals 1, it's a 0. So what do you get here? Is it 3 times x minus 1 times negative 2, correct? So that one is negative 6 times x minus 1. So around x equals 1, the px, if you zoom in, the polynomial, this degree 3 polynomial, behaves a lot like this line with the slope negative 6 and x-intercept 1. Okay? So I want you to go ahead and compute this, your exercise number 2. Is that right? Yeah, 2. The approximation for x equals 3. Around x equals 3, how does this px behave? What is this one? All right, was it okay? 10 times x minus 3. So we go now to use this approximation to sketch the graph of the function. Use them to sketch the graph. Right, here's x-axis. And I'm going to plot those zeros. Zeros are negative 2 here. And negative 1, 0, and 1 here. That's 1. And 2 and 3, that's 3 there. Good? So the graph of this function px is going to cut through those x-intercepts, right? Because they're 0. So how is it going to cut through at around x equals 3? Our conclusion is that around x equals 3, px, if you zoom in, looks like a line with a slope 10 times x minus 3. So that's x-intercept 3 there, so must be slope, slope 10 line like that. So that's how it looks like around there. So I'm going to write around there, it looks like 10 times x minus 3. Fair enough? How about around 1? Is a negative 6, right? Negative 6 slope is like this relatively. This negative slope. Y equals negative 6 times x minus 1. Good? And what happened around negative 2? It's positive 15, right? It's positive 15. Y equals 15x plus 2. That's all the information we have from the near zero, right? What is really happening in between negative 2 and positive 1, or 1 and 3, is you can plug in some numbers, or you can do other analysis, which is called calculus. So you will learn more about how to take care of in between more rigorously in the calculus. But right now, we're just going to make a wild jump in here and conclude that nothing mysterious thing happened. You just have to turn around nicely like that to make it as simple as possible. All right? So is that direction. So to connect it, you just have to connect them like this as simple as possible. At least it gives you some idea with this slope happening around that value, how high it might go up to connect it and things like that. So that's how you sketch the graph. All right? To summarize, I didn't give you a logical explanation to how to connect these two in the middle to as simple as possible. That's what I gave you. Fair enough? All right. What is inconvenient about this one? It's not factored, right? It's not factored yet, so we have to factor it. So degree 3, you try to factor. The strange thing is that this constant term is not there, right? So when you apply rational zero theorem, and it's kind of weird. But it's actually good, because x is always a common factor if there's constant terms missing, right? So we can factor out x, correct? Once you factor out x, you're left with just a square, quadratic. So you can factor it. So first, factor this polynomial completely, then use the technique that we've been doing. So once you factor it out, looks like there's 3 distinct linear factors. None of them are equal to each other, so there's no multiplicity higher than 1. Okay? Then you look at each 0, -1 is the smallest one, and do the approximation. And simplest approximation seems like 4 times x plus 1. And x equals 0, -3x, x equals 3, 12x minus 3. All right, use that to sketch the graph of this function. All right, was that okay? Any question? Very good. All right. So here's another one, and there is a difference to this, and something is different about this one. So let's take a look. This one also misses a constant term, right? But what is a common factor this time? We're going to do the same computing approximation near zeros. And px is factored out by which factor here? X squared, right? X squared. So it's x squared there. And you're left with a -2x squared minus x, one copy, and plus 3, right? Not comfortable with having a negative leading coefficient, so I'd like to factor out negative there. X squared, and this becomes 2x squared plus x minus 3, right? As you factor out negative. So you see the factorization of the quadratic part? Maybe it has to be 2x, must be. So we want 3, and so I think it should be over here. 3 and -1. Is that right? -3, -2, positive 3. So that factorization works. Make sense? Alright, that's complete factorization. What's different about this one is that multiplicity, right? Here's a linear factor, and there's a linear factor, and there's also a linear factor in here, but it's squared. So how many zeros do you see? 3, right? So the one is, what is the smallest zero here? But negative, right? -3 divided by 2. Fair enough? Right. Let's do that part. What is the second largest in the number line? X equals 0. So that part here you can look at as x minus 0, raised to second power. So that's a 0. Y is 0. Right? What is the third one? Positive 1. These are the approximations, right? So let me do this 0 part, because that's quadratic part in there, right? We don't want to plug in x equals 0 to that part, right? Because it makes everything 0. It's too much simplification. So don't touch that part. Then evaluate x equals 0 here, and this part is a -1, correct? And if you plug in 0 here, you get 3. And what do you get? This negative x squared is, what it means is a negative and x squared inside here like that, right? That's what that means. So is negative still there? Negative together is a positive 3x squared, right? This time this is not a line, right? Remember how the 3x squared looks like? It's a parabola upward there, concave up. So at x equals 0, it looks like that, right? Not crossing it there, right? So I want you to go ahead and compute the approximation of the other two cases, which are linear, so you will end up at the same linear case. And together all, try to put into a graph. Right? It's a slightly different graph, and use your imagination, at least matching these near zero behavior, and try to connect them. So that's completing that whole thing is your exercise number 4. All right, does that make sense? Which top? This connection in here? This first line? This 2x minus 2x plus 3 is the factor if you plug it into 0, so you don't touch that. But the other two factors, here, you plug in this number in there. Right, that's 9/4. This one here, if you plug in -3/2 minus 1, yeah, that's -5/2. It's written here. Yeah. Any other question? This one's conveniently all factored for us. However, it has all high multiplicity, and try to put those high monomial shape everywhere and see if you can sketch it. This is, what's the exercise number? Exercise number 5. Always the first question is to compute the approximations near zeros. You write them down and think about how the fourth power monomial looks like, third power looks like, second power looks like, and put them all together. So approximation at around -1, got the square coefficient -27, right? Around 0, there's a fourth power of that 0 factor, coefficient -8. Around x equals 2, it's 144 times the cubic power. Any question about this calculation? If not, let's use this one to sketch the graph. So try to sketch the square shape around -1, but there's negative coefficient, right? So how does this one look like around -1? Not upward like this, right? It's a downward because of -27. Fair enough? So try to sketch it. And if it is high power like this, you know it has a little bit of flat part in there too. All right, does that make sense? Yeah, it's but you have to remember how the fourth power looks like and third power looks like, and deal with that sign of a coefficient basically. Right? Any question? So that's what we mean by the near zero behavior, and use that to